This is a video lecture for Math 181 for Tuesday, April 28th. And the topic today is calculating volumes by cylindrical shells. For Monday's class, section 6.2, we talked about calculating the volume of various solid objects by dividing those objects up into a series of slabs and calculating the volume of each slab, summing up the slabs and getting the total volume. I want to consider a specific problem here. Suppose we had the function y equals x minus x cubed, okay? And I've created a very simple graph of this function from x equals 0 to x equals 1. Let's suppose we wanted to take this curve and rotate it about the y-axis, not the x-axis, but the y-axis, okay? And calculate the volume of the solid created by doing that, just rotating this part of the curve about the y-axis. Well, as you see, you would get some kind of interesting kind of donut-shaped object. I want to calculate the volume of this. Let's use the techniques we learned about in the last section. So what we do is we create a horizontal slab because we're rotating around the y-axis. And let me label the axes here because it should be obvious. This is the y-axis, this is the x-axis. And what I do is I create horizontal slabs here. And it turns out I'd actually get these slabs, if you rotate them around the y-axis, you actually get a series of washers, right? A series of washers. So what we could do is calculate the volume of each washer and then add them all up. And we already talked about how to do this. This slab would have an inner, or washer would have an inner radius x sub I and an outer radius x sub O. Okay, and so this is kind of, if we took this washer and then we flipped it over and we're looking at it face on, this is what we get here. We have an inner radius and an outer radius. And as we talked about, the area of this washer would be pi times the outer radius squared minus the inner radius squared. And this is all well and good. We talked about how to do this, and we know how to do this. There's a problem, though. The problem is, in this case, we have a function y. Y is a function of x. But we would need to solve this equation for x and plug in for our x outer and x inner. So we need to solve this equation for x so we can plug in for x and turn this into a y equation. We really want the area as a function of y. The area of each washer is a function of y. The problem is we have a cubic equation here. And this is very difficult, if not impossible, to solve for x in terms of y. So we want to solve x in terms of y. But I dare you guys to try that with the cubic equation. Could you isolate x? Very difficult, right? I've got y as a function of x, but to find x as a function of y is challenging. So this problem becomes challenging, and it's not obvious how we can do this problem. So this is the motivation for using a different technique to calculate the volume of a solid of rotation. It's called a solid of rotation because we're rotating this curve around the y-axis. So we're going to use a different method to try to calculate the volume of this object. And here's how this method works. It's called the method of cylindrical shells. So instead of dividing this curve into horizontal slabs, what I'm going to do is divide this curve into vertical. Start by taking this curve and divide it into vertical rectangles, just as we did to try to find the area under the curve. So let's imagine we divide this curve, and I've drawn most of these in dashed lines, but one of the rectangles in solid line. We're going to divide this curve into a series of approximating rectangles. And let's focus in on a particular rectangle. Okay, this rectangle will lie at a distance x sub I. By the way, this x sub I is not x inner, it's actually just the ith rectangle. So this I stands for the ith rectangle. So this rectangle is a distance x sub I away from the y-axis. Okay, the rectangle has a width of delta x, and the rectangle has a height of f of x sub I. So the value of the function evaluated at x sub I gives you the height of this rectangle. But we're not interested in calculating the area under this curve in this case. What we're actually doing is we're trying to calculate the volume obtained by rotating this curve around the y-axis. Well, now let's think about this. If we take this rectangle and if we were to divide this curve into a series of rectangles and just focus on this rectangle, as we rotate this curve around the x-axis, this rectangle, rotate around the y-axis, this rectangle would be rotated around the y-axis, okay? this rectangle would rotate around the y-axis. It's kind of hard to demonstrate that because it's three-dimensional, but it would rotate around the y-axis. Okay. What shape would be created by rotating this rectangle around the y-axis? The shape that would be created is a cylindrical shell, right? It would be a cylindrical shell. So this is taking this rectangle, rotating it around the y-axis. Okay. The shell would have a thickness, delta x. It would have a radius of x sub I. And it would have a height of f of x sub I. So what if we think of if we rotate this curve around the y-axis, we create some kind of solid of revolution or volume of revolution. What if we think of that volume of revolution as a series of nested cylindrical shells? And then let's try to calculate the volume of each cylindrical shell, and then let's sum up all the volumes of those cylindrical shells to get the total volume of this volume of rotation. So that's the idea behind the method of cylindrical shells. So again, if we focus on one rectangle, we get this cylindrical shell. And now what I want to do, I'm going to erase some things, and we're going to try to figure out the volume of just this cylindrical shell. So let me erase what's above here. And let's imagine that we take this cylindrical shell and we take a pair of scissors and we just cut it. It doesn't matter where, but we cut it vertically. We cut it vertically, so we peel it out. So we cut it and then we flatten it. We're going to flatten this, kind of steamroll this cylindrical shell. And what we would obtain, so if we cut and flatten it, if we do that, we're going to get a big slab like this, okay? And I'll draw it right here. It's going to be fairly long. Sorry, that wasn't exactly straight. This is what it will look like. Okay, if we cut this and we spread it out and flatten it, we get a long slab. The slab has a thickness. This thickness here is delta x. Okay, the slab has a height of f of x sub I. Now, what is the length of this slab? Well, the length is basically the circumference of this circle, right? Well, this circle has a radius of x sub I. So what is the circumference of this circle? It's 2 pi. So this length here is 2 pi times x sub I. Okay, so that's pretty cool. And now that we can calculate the volume of this slab just by calculating the volume of a rectangular shaped object. The volume is just the length times the width times the height. So the volume of, I'm going to call this the ith slab. The volume of the ith cylindrical shell, the volume of the ith cylindrical shell that makes up this solid of rotation is going to be equal to 2 pi x sub I times f of x sub I times delta x. Okay, that's the volume of the ith cylindrical shell. And we're thinking of our volume of rotation as a series of nested cylindrical shells. Okay, that's the volume of the ith shell. Now, how do we obtain the volume of not just the ith cylindrical shell, but the volume of the total volume of the solid of rotation, which we're thinking as a series of nested cylindrical shells? Well, basically, we sum up the volumes of all these cylindrical shells. So the total volume, this should be an approximation. The total volume of our solid of rotation will be the sum as I equals 1 to n of each cylindrical shell, which will equal the sum from I equals 1 to n of 2 pi x sub I times f of x sub I times delta x. Okay, so that's the approximate volume. We're approximating the volume of this solid of rotation by a series of cylindrical shells. Now let me erase what's down below here, and we're going to come to a formula we're going to use. Okay, now this is only an approximation of the volume. The way this becomes exact is if we take the limit as n goes to infinity. So just as with finding the area under a curve, if we force the number of rectangles to go to infinity, that approximation becomes exact. Well, if we force the number of cylindrical shells to go to infinity, that volume calculation becomes exact. So the volume is exactly equal to the limit as n approaches infinity of the sum from I equals 1 to n of 2 pi x sub I f of x sub I times delta x. Okay. And then now I'm going to think of this. I'm going to think of this 2 pi x sub I times f of x sub I. I'm going to call this the function g of x sub I. Okay. Now, if you guys remember, this is just the limit as n approaches infinity of the sum from I equals 1 to n of some function g of x sub I times delta x. Okay. This is simply the definition of the definite integral of g of x sub I. This is go back to chapter 5. This is just the definition of the definite integral of this whole function. So I can write this as the definite integral from a to b of g of x sub I times dx. So our delta x turns into dx. But g of x sub I is just equal to this. So it turns out the volume of our solid of rotation is equal to the integral from a to b of 2 pi x sub I times 2 pi x times, I wrote this wrong. It's a mistake of mine. This should have been g of x here. Excuse me, just make a note of that. I wrote this incorrectly. Let me call this should be g of x sub I, but this just turns into g of x, not g of x sub I. And so what happens is this function, g of x, is actually equal to 2 pi x times f of x times dx. And so this is our magic formula for calculating the volumes of, pardon that slight mistake there. I should have been careful transitioning from x sub I to x, okay? So we get the definite integral from a to b of g of x dx, and but g of x is equal to 2 pi x times f of x, and so the volume of the solid of rotation is equal to the integral from a to b of 2 pi x times f of x dx. Okay, this is now the formula. So this is basically a theoretical motivation for this formula. Now we're going to use this formula and apply it to two specific example problems. That'll be in part 2.